and this is the solar thermal and photovoltaic water heating session. We're going to have three speakers: Henry Vandermark, Carlos Colin, and Zach Vetter. Let's get to it.
Hello, I'm Henry Vandermark. I run a company, Solar Wave Energy. I was an installer for 30 years, and then in the last 15, we've been monitoring solar thermal systems on a web-based platform we've developed. And I'd like to show you tools that we have to help systems go more efficiently. On this slide, you have a couple of drainback systems, flat plates on the left and evacuated tube on the right. They're both drainback, and they're both multi-array systems and have been monitored for 5 or 6 years. And my slides won't advance now. Okay. We also monitor solar photovoltaic systems and PVTs. So I often get asked, why not just PV? Solar thermal is a lot more efficient per square foot. These slides will be available later, so you can look at the stats of it. As all of you are at a hot water conference, you know, hot water is a load, and load is a target and what we should get paid for. So our job is to use solar thermal to offset the loads for domestic hot water, laundries, processed heat, etc. Collectors come in a number of different flavors. Flat plates are what most people are familiar with. They're black box. It's old technology. Arrays of collectors on a roof add up, and we then put them up in certain size arrays, and depending on how large they are, the balance of them becomes more important, so that if you put too many together, you might get hot spots, and if you don't realize it, you may not get any production out of them. Evacuated tubes are also part of the marketplace. They run a little bit higher temperature generally, but they're not quite as efficient per square foot per year, but they do better in more severe climates. We also monitor other building inputs, such as a solar wall on the left, or passive additions, since we're trying to balance the building's energy use. Pool panels are not just for pools. A lot of times flat plate unglazed panels get used for processed heat. The picture in the bottom right is a meat processing plant. Large system heats a huge amount of hot water for meat processing. I won't show too many curves, but this is one of my favorites. It came from Home Power a long time ago. It's an efficiency curve of collectors. The left-hand side is the peak efficiency, which means the time when the outside ambient temperature is the same as the interior temperature of the collector. Hence, it's not really losing any heat, so that's a peak efficiency. The steep curve is a pool panel, drops off very quickly when it gets cold outside. The more graceful ones are evacuated tube. It drops off more gracefully when it gets colder. But in any of these, you want to run your collector at the points on the left-hand side of the curve. PVTs or PV therms have come into the marketplace. They're basically a heat exchanger of some sort on the back of a panel. They skim the heat off of the PV cells. They can be used for nighttime cooling as well, dumping heat, but they cool the panel, increase the efficiency of the PV cells, and reheat off of the panel. About the equivalent efficiencies of pool panels, but if used in large areas with heat pumps, can draw off a lot of heat. This shows, and you can take a look at the slides afterwards, so it's the efficiency change with added. You can get a increased PV as well as a lot of thermal load. In these cases of PVTs, we monitor both the PV as well as the hot water component. So we're monitoring both the balance of strings for fluid as well as for strings for PV. One of the ones we did was a casino out west where they had multiple trackers, a 35,000 gallon tank. And since it goes through many seasons, sometimes the heat is used directly for domestic water. Sometimes it goes through a heat pump. So being able to manage that is important through the year. And they use a modulating heat pump that allows you to have a 25 horsepower heat pump, and sometimes it's acting like a 5 or 7 or 12 horsepower, but it enables you to adjust the flow, and we're able to help them monitor that. System types, mostly direct systems aren't used that often unless you're in warm climates, but they are very efficient because you're getting direct heat. Drainbacks or closed loops are mostly used, and the main goal in this case is to cool the collector rather than, you're not really trying to heat the water, you're trying to cool the collector in the sense you're heating the tank. The goal in any of these is displaced energy. We measure production, the collector off the roof, or contribution, the amount of energy that's delivered to the building, but the amount of energy you would have otherwise consumed, or the displaced energy, is really your goal. If you have a power purchase agreement, it's based on savings, and the savings are really reducing the amount of money that's spent. So when we monitor this, we want to keep that in mind as a target focus. So that those are the bottom lines. We can monitor and we can measure the production or contribution or backup contribution. But BTU meters are complicated, expensive, and really the only BTU or revenue grade meter is really the revenue grade meter you pay for. So that if you go to a gas station, that gas pump is your revenue grade meter. On your house, building, kilowatt meter, the revenue meter is the one that counts. So when we're measuring this, we cross-reference it with that data, so we get the numbers off of the revenue meter, either in a data feed or separately. But without having that, you don't really have a bottom line. The accountant will say your meters are fuzzy, but if you cross-check them with the revenue meter, you substantiate your meter, and you're making net energy, and they're talking sort of gross energy, so that if you're able to substantiate the what's offset, you're doing a lot better. We monitor a lot of the behavior in systems, so that the balance of systems is important. People supply a working drawing, and we make it into a live diagram with live temperatures, so that this shows the balance of different arrays on the roof and different data points through the system. This system has a secondary transfer loop between the solar tank and the backup tank, so that it wouldn't let the backup tank get heated by fossil fuel if the solar still had energy in it. It doesn't just require it to be pulled through, but like on weekends or off season, it would make sure that the backup boiler wasn't firing. In some cases, we had a school that during the summertime, they didn't have any load, but they had a recirc loop, so that there was no, quote, production in the summertime. It had a big solar tank, an injection system where it would inject heat into the flow of the cold water going to the hot water tank. But hot water tanks would be heated separately. There's kind of a line in the sand, or line on a drawing between what's the solar guys and what the building does, and they don't necessarily talk to each other, and that's one of the major problems in some systems. So that in this case, the solar tank was hot and the other ones were not. And what happened is in the summertime, the line at the top shows the tank is hot through those months, but there's no production. It shows only 87,000 BTUs per square foot, which is about half what it should be. And that's just because they did not take advantage of the heat and they were probably burning some gas or something otherwise. We also monitor and warn about different kinds of anomalies. Steam back is when a system is shut down because it's overheating. This one shut down and got up to 97 pounds pressure, which is kind of high. This is a drawing that was supplied to us, but it shows you could do a drain back, but in the case that this drawing shows on the upper right how it was as drawn, piped in a way that everything would drain through the way that it came in, or either the supply or return. And as built, it was trapped. So every time it stopped, it would have to boil the fluid out of the collectors rather than just pushing it back down to the bottom. This is a slide of the that initial drain back on the left from this top slide, and it shows the tools that they have to be able to see what each manifold exit point on the roof is, so they can tell that those are balanced. Multiple loads. They have, some systems might have a pool and domestic hot water, and you want to be able to manage the priorities and know that something is changed. During COVID, there was different schedule changes, so that universities and academies that had large pools would not have the same kind of hours, so that being able to switch that remotely is nice. So this one would save a certain amount of energy in the storage tank, so they could deliver hot water to the house, to the building after the sun goes down. We all have issues. Some solar systems have issues, and you want to stop them before they become a problem. Some issues are outside of your domain. A lot of times there's valves or things on the building side that you can't control, but you need to be able to sense. This loop that goes from the solar tank to the building should go cold in, hot out, as it does on the left, but on the right it is hot in, cold out, meaning that there's some valving that's been changed on that side. You can't really change it, but can at least advise people that there's a problem there. We also monitor the runtime of backup boilers so that you can tell whether things are duty cycling properly or not. Cycling is a big problem. On and off is not the way to run a system. We did a little sampling and found that of a certain group of systems, many did 10 or 20 more cycles per hour sometimes. So that if it's cycling on and off, it means it's just dumping heat out. It's not really doing much. So like many things, it's you build it right. Keep it simple, stupid is the old KISS principle. While I'm a solar plumber by trade, the kind of make it simple enough so even a plumber can understand is sort of the way I kind of think about it. So, and make the building and the building system and the solar system work together. If there's a building automation system, the installer should have either access to that, or the building automation system have access to the same monitoring as the installer. The installer is the expert in this case. The building automation and management system may have a bigger view, but they may not know the details of a solar system. Measure the impact, and if there's some questions, or if there's some way you have questions, please email me later, or be happy to entertain any from people who have been at the conference. Thank you.
Henry, thank you. Did a lot of information there. I'm going to have more questions for you later, but we should give Carlos Colon some time to talk too. So let's move on. Carlos.
Okay, I'm going to share my screen. Hello there, my name is Carlos Colon. I'm with the Florida Solar Energy Center, and I'm here to present a large capacity residential PV assisted heat pump water heater. On the screen, a little background about myself and the activities I've been performing in the last 10 plus years in terms of water heating. Currently, we are testing connected heat pump water heaters on the bottom. That's the picture shown on the bottom right. Connected to CTA 2045. Here is a list of a history. This represents a history of various different types of water heating systems that we have tested at the laboratory. And the goal here is to try to reduce consumption to zero. I have achieved about 1.2 kilowatt hours per day with a 50-gallon heat pump with PV under a family realistic load. And the system I'm presenting today, the 80 gallons, beats that, so that getting closer and closer to zero energy water heating. This is the original prototype system that we tested back in 2016 and I presented in 2017. It had a staged electric heating where when the compressor finished heating at 12 o'clock and 12 midnight, 12 in the afternoon, stage heating was kicked in to pump more energy into the tank past 140 degree water. So today's presentation, PV assisted 80-gallon heat pump water heater. This research activity was funded by ASEC in support of U.S. patent filing. Manufacturer Bradford White donated the 80-gallon heat pump water heater. The system utilizes two photovoltaic panels of about 300 watts peak. The newest thing here is we developed a current detection circuit and controllers so that in place of a lower controller, which was previously utilized, which is a little bit more costly. For simplicity of operation, the heat pump was operating only on compressor mode. No stage heating was utilized, and I'll talk a little bit more about that later. And the PV assisted heat pump water heater utilizes a mixing valve that's set to deliver water to 125 degree Fahrenheit. So today's presentation, here it is pretty much a variant of what I've developed before, except now we are using an 80-gallon heat pump water heater. The stage heating by using the bottom element was not utilized because when a heating element is changed from what comes with a factory fitted, the unit does not recognize it and it starts beeping. So basically, I decided just to run the heat pump water heater itself with its native controls and keep it simple, with the assumption that larger loads are going to be imposed on this system, so that compressor will run longer and therefore no need for electric resistant heating. A little bit about how the controls work. Basically, we detect the current coming out of the microinverters, and with a current transformer, a 5 amp current transformer, and the circuitry rectifies and converts that signal into a voltage output that a microcontroller that has an analog to digital converter can read, and then make a decision whether to raise the thermostat setting on the heat pump water heater or go back to the normal setting, which I consider that to be 125 degrees Fahrenheit. Here's a few examples of the programmable control logic that this controller can manage. We can set the thermostat back from 125 to 120 at night if we want to, assuming that we have stored enough heat in the preceding day. We can set the thermostat back to 115 degrees Fahrenheit to allow the sun to come up and utilize the solar resources better. We can go back to 125 degrees Fahrenheit anytime. And we can set the thermostat to 140 degrees when power is being generated by the photovoltaic modules. In this case, a programmable threshold of 100 watts or more. So for a complete year, what we did is we took the baseline hot water load, which is shown on the top right, a small plot. And throughout the year, we put a multiplier. So, and during some weeks, we said, let's double that. So every event will be double of what the original hot water load was. And we kept changing that throughout the year, 1.5, 0.5, 0.8, 0.9, basically adjusting the total daily hot water gallons, which on the bottom left screen can be as high as 110 degrees, 108 gallons per day, not degrees, 108 gallons per day, and as little as 30 gallons per day. So here's a typical power consumption of the unit. Notice that the new generation of heat pump water heaters are more efficient than the older ones. Before we were reaching 700 watts. Here we are reaching about 450, 475 watts with a full tank of 80 gallons at 140 degrees Fahrenheit. And here's what happens when you add PV to the system. That's represented by the yellow curve on the left plot. And on the bottom right plot is the net energy consumption that this heat pump water heater is utilizing for heating water. So barely a peak of 300 watts at the end of the day. So we observe on the highest load where we were exposing the heat pump water heater to 108 gallons per day. We wanted to find out where does the delivery water falls below 110 degrees, which is what I consider to be the critical delivery temperature. And at 108 gallons per day, and in some parts of the morning, yes, we went below that level. And when the unit was submitted to about 80 gallons per day, I only saw one day when we went under the 110 degree levels. All the other loads of 60 or 50 gallons per day perform extremely well. So the target and goals for this is, as I mentioned before, is to provide water heating for a family for less than a kilowatt hour per day with 80+% energy savings over electric resistance, minimize electrification, maximum carbon reduction, increase energy storage, ultra high efficiency performance, reusable PV modules. In the case the heat pump water heater is replaced after 10, 12, 15 years. You can reuse the PV modules again because they have 20, 25 years of life. And extended run times, which for the southern states, southern areas in the country, cooling can be a benefit. Also, this system presents a serious competitor to solar thermal systems where there's no freezing to worry about, no pumps, lower cost, and minimum maintenance. The slide shows a approximate retail cost of the components to assemble an 80-gallon heat pump water heater assisted by two PV modules, somewhere about $4,500. No, not including installation. So results vary depending on the solar radiation for the period and depending on the load imposed on the water heater. We saw extremely high coefficient of performance efficiencies all the way to 27. Minimum efficiency is about 7.7. And here we have a plot that kind of depicts by average gallons per day what electricity consumption and the amount of solar electric produced by the photovoltaic panels. In general, if we regress all this data, we can clearly say that if you're providing 80 gallons per day, you're going to, on average, you're going to consume about 0.9 kilowatt hours per day. So we have basically met or exceeded the goal of 1 kilowatt hour per day of electricity consumption for heating hot water. Drawbacks of the PV heat pump water heater, well, premium parts, they cost over $4,000. Wiring between the current sensor and the controller, because we usually put the current sensor at the electric panel distribution of the house. However, this can be solved with wireless signal to the controller. Net metering agreement, because the inverters do provide, they do inject power into the grid when the power is not being used by the heat pump water heater. However, this can be solved with a refined design on the controller, annual certification, install permit cost. I don't think there's not much we can do about that. Of course, the roof space or racking cost for the PV modules. Warranty, that depends on a manufacturer. If he would allow warranty on a system that includes photovoltaic assistance to it, and perhaps accelerated annual rod depletion, because we are elevating temperatures towards 140 degree Fahrenheit levels. Supporting literature, you can find this at the AFSEC Publications Archive. They are listed. In particular, the second paper, it was a paper presented at ACEEE conference, and it includes simulations for various regions and cities in the country, and you can analyze what photovoltaic assisted heat pump water heater can do with 2 and 3 PV modules for those cities that are in the colder northern region. What we envision for a commercial or refined concept, in this case, we would love to bring the AC lines from the microinverter to the heat pump water heater as opposed to the electrical panel, and make all the connections at the heat pump water heater to simplify things, and have a smart inverter so that it detects when the heat pump water heater is off and it doesn't inject to the grid, in case we can certify this system as a non-grid injecting and simplify the permitting process. Any questions, please contact me at carlos@fsec.ecf.edu, and we acknowledge that this research was possible with donated equipment from Bradford White. We really appreciate your support. Thank you very much.
Carlos, you gave us a lot to chew on there.
Yes.
Thank you. Lots of good information to dig into.
We've worked hard at it for the last 2 or 3 years. Trust me.
Yeah.
Especially with the patent process.
I've done a little research along those lines. I think I understand. Anyway, thank you. Well, we're going to move on to Zach Vetter and see what he's got for us.
Hello, Larry. Thank you very much. Hello, my name is Zach Vetter, and I'm here to talk to you about a solar thermal system that I've built with the help of Larry Weingarten. I am an energy enthusiast who've had the opportunity to meet Larry and learn from his examples and his knowledge, which has been a lot of fun. And I want to talk to you a little bit about the state of solar thermal and what kind of issues it's had and where we are. So conventional wisdom today is that, at least for domestic hot water, solar thermal directly has a lot of barriers. It has a high initial cost. It's kind of complicated to care for and maintain with valving and piping, sensors and such. And even if everything's done right and is made as simple as possible, as other people have mentioned, it oftentimes only contributes 50 to 70% of the total energy, necessitating conventional or other backups to begin with on cloudy days. And further, even if you do a good job of implementing a system, there's still a lot of other long-term real problems with it. There's storage failure concerns with class line tanks, with anode rods failing. There's a myriad of control sensors, which, if they're not installed properly, even if the design is right, can lead to catastrophic system failure, freeze, and overheat damage. On top of that, this complexity leads to people not wanting to deal with maintenance, deferring it, or even just neglecting it entirely, which the same result happens. And then finally, there's issues of practicality. Like, at some point, you're going to have to re-roof your place. And you look up there and you say, oh gosh, what am I going to do about this confusing thing that I don't know how to fix? So there's a lot of barriers to it. Now, I didn't know all this. And I walked up to Larry back in 2014 and said, Larry, I want to design a solar thermal system for heating water on the house. And I want it to heat all of the water for what I want. I want hot water whenever I want. I don't want any extra maintenance. I want this thing simple and reliable. And a lot of you are probably thinking, oh, great. But Larry very kindly did not do that and sat down and started to talk to me about things, about what the options were. And over a period of about 6 months, we worked out a design that I think is very interesting and has a lot of really neat potential. So the design goals for this system. Right up front, there was a couple of musts. Compared to what I had, which was a 20-gallon resistance electric heater from GE, which provided hot water, I wanted to make sure that this thing we built, it absolutely had to use less energy than the previous system. Not even a question. It's a failure if it didn't. It also had to be equal to or less maintenance than the previous system. I don't want to be cleaning panels. I don't want to be changing filters. I don't want to be watching for hot and cold. I don't know. It needs to be as much work as an electric water heater was, which really wasn't any work at all. And finally, it has to provide a greater quantity of hot water than what the old system did. I want more of it. 20 gallons was a little skimpy for myself. Beyond that, there's other things I wanted the system to have, but we'll wait and see how it works out. It really should be overall cheaper to install and operate over its lifespan. It's okay if it's expensive up front, provided its maintenance cost or its life cycle cost is very low and justifies it. It really should be simple enough that even an unskilled homeowner like myself could deal with. Not a plumber, not a technician. You want something that you really could have the homeowner take care of and not be afraid of. And finally, whenever possible, it should be made with off-the-shelf components that are mass-produced. Something that, it's not hard to find this thing. You can go buy it anywhere, and they make millions of them. A good example would be fuel injectors for cars. When they came out in the 80s, kind of a mess, not that great. But after 20 years of making billions of them, even though they're quite complicated, we're pretty good at making them now because you've made so many of them. You can buy them off the shelf. They work great. There's lots of examples like that. There's, pumps from Grundfos or just invincible, simple things. So the point is, make it as much as possible out of cheap, mass-produced stuff that can be found anywhere. So when I sat down with Larry and looked at a possible design, very quickly he directed me over to this thing made by Gull Solar, which was a thermal system based on an old Sunburst design, which is essentially a bunch of HD polypipe wrapped in a circle as big as you wanted. In this case, these were 6-foot diameter pipes, and with a little glazing over the top to protect from wind, run into a storage tank, an existing water heater. And there's some basic benefits to it. The poly pipe is freeze tolerant. If the water freezes in the coils and expands about 9%, poly pipe doesn't care. It handles it very well. Further, HD poly pipe is very UV tolerant, highly resistant to the sun, just extremely longevity, great longevity. Interesting characteristic about these designs is that the coils are pretty inefficient by solar thermal standards compared to heat boxes with, black carbon coils inside of them. These coils really aren't that efficient. And that's actually part of the design, intentional design. They can be scaled together, but they don't, the hotter they are compared to the outside temperature, the poorer they do. They tend to bleed off the heat. And in our experimentation of these things, they've been on the roof above me for the last 7-8 years. They really don't get above about 170 degrees, even in direct sun, stagnated. They do freeze, but I don't care. It's great. So we made some design changes to the basic idea of what was on that previous slide. First, we went for a really large tank. My logic was, look, if we have a huge tank, then you've got more water to work with. You can't rely on hot water all the time. And if you don't have hot water available all the time, you're having to make it on the spot. That's not realistic. There's days that are sunny, there's days that aren't. Well, if I could have a 500-gallon tank, what do I care? Just have a huge buffer. The largest tank I was able to find with Larry's help was a Marathon 105-gallon commercial resistance electric water heater, which is pictured on the left. And it's just a straight electric water heater. So, but the interesting thing about it is that it is entirely plastic and fiberglass. There's no metal in it. I didn't know this at the time, but many of you would understand there's no anode rod. And without an anode rod, there's a massive reliability increase. There's no issue of the water eventually eating through the glass-lined tank if you forget to replace an anode rod. There's no stench or aging of the water that occurs in the tank. I didn't realize what a design decision it was, but I'm glad Larry did. And the second thing we did on the right is we asked for more panels than we should have had. If you do the math of how much solar roof space you're supposed to use for 100 gallons of water, conventional wisdom would say about 75 square feet. I said, give me 100. My logic was, well, the coils can't overheat. And if we have too many of them, it just means that it heats faster. And on days when things aren't ideal, maybe it heats a bit more effective than it would if it only had 75 square feet. And finally, we went to great lengths, as you can see on the bottom two pictures, to insulate all the tubing. It's mostly made of poly or PEX. And this is an example of the 3/4 inch PEX pipe that has 2 layers of insulation. It's huge. It looks like 3-inch pipe when it's all done, but it's this little nothing thing. Anyway, we did not want to lose any of the heat transferring between the tank and the collectors and going back and forth. So with Larry's help, we went and installed this thing. This is installed on a south-facing roof in Carmel, California. The degrees on the roof is about 18 degrees. It's not perfectly arranged for uniform solar summer and winter production, but that's okay. The neat thing about the coils is that they have, since they're a bunch of hemispheres, they actually handle different degrees of the sun showing up pretty well. And this is an example of the tank with its outrageously huge insulation all set up and a differential controller and the pump to push the water back and forth. So it's all great. I wanted to run this thing without any backup heat the first year to see how this worked out and to find out how well it worked. And unsurprisingly, I wasn't able to have 100% solar heat without any backup heating. This was the worst day of the year that I intentionally showed. In the graph, the 2 yellow lines represent the only section of sunlight that happened in a week. And you can see from the temperature differences that the tank eventually got a little too cold for me. But it was really neat to find out that practically speaking, over the course of a year, there wasn't any more than about 15 to 25 days where the water tank did not produce hot water enough for my needs. And my testing was very simple. Either I took a shower and I liked it, or I didn't like it. It was sort of a pass-fail. Everybody's a little bit different, but I thought this system is for me. If I turned on the water and I couldn't make the water warm enough to my liking, that's a fail. And it worked out pretty well. Most of the year, it looked more like this. This was back in the equinox. You can see that, yes, there was a little bit of decay every day from the tank, but that Marathon tank was very, very energy efficient. It was one of the best efficient tanks in the market. It only lost about 7 degrees Fahrenheit per 24 hours. And the solar thermal would push it right back up. So I generally have had an extreme excess of hot water available at all times. I won't go over this slide much in the interest of times, but this is kind of a breakdown of the sensors we put in place on each coil and looking at a single solar day where the temperature of the coils, the outside air, the temperature of the tank as it goes up in time, you can see what it did, plus a shower I took. It's very neat. But it kind of shows how the system works and the energy it consumes, which is largely just the water pump. So there's some potential concerns about this system and mainly about Legionella. After all, it is a major health issue. And how are we doing with a thermal system that has temperature ranges in the 90s, 100s, 110, ideal growth period? After 4 years of running the system, we decided, well, let's take a sample. We drained the bottom of the tank where all the particulates would build up, as you can see in that unflattering water sample on the right. Took it over to the health department, gave them a test, and they said, no, there's no material in blouse. There's no pathogens we found. So at least from that respect, I think it shows that it's been a pretty safe system. The big things about this is that it did what I wanted, not quite everything I wanted. It does provide hot water whenever I want, for any length of time I want, and it does do it year round. In the wintertime, I need some backup heat. My backup heat is the top element of the Marathon water heater. And I have measured the total energy consumption annually for the whole system. I don't use more than about 150 to 200 kilowatt hours of energy in resistance heating on the backup system. In fact, I use the same amount of energy basically on the pump yearly. The pump, recirculating the water over the course of a year, uses about 120 kilowatt hours. So it's a very, very low energy system. Almost all of the energy, 90%, is provided by solar thermal, largely because the storage system allows it to coast between times of production and use. What I found over these last 8 years is that I can basically shower whenever I want for as long as I want. And it's just me, but that's fine. I like my showers. It really doesn't seem to care about massive demand changes. Remember, it's a 105-gallon tank for a single person. So if 2 or 3 or 4 people wanted to show up and shower in a single day, it really makes no difference. The pump doesn't really know the difference. In fact, it works better when you have cold water going in. The solar thermal does a great job of heating up cold water. There has not been any maintenance. I have not gone up on the roof to clean the collectors or change sensors or filters, or I don't want to do any of that. I don't have to mess with it. And largely the operation costs of it are fixed. Whether I take a shower or we take 5 showers in a single day, the pump comes on when the sun comes out. It circulates the water, runs for 2, 3, 4 hours at most, and it puts it back in the tank. Whether I take a shower or not, that happens. It's entirely based off of a sensor that determines if the air or the temperature of the water on the roof is greater than the bottom of the tank. It doesn't seem to care whether I use it or not. So whether I use a lot of water or very little water doesn't affect things. And this is really what I want to do. This is the bigger, deeper issue. I want to design things where the end result is better than what you had before. There's a lot of talk about reducing energy, and that's an important thing. But usually it comes at the cost of comfort, at the cost of quality of life, at the cost of simplicity. And I don't think we need to settle for that. We can have our cake and eat it, provided we build efficiently. Choosing to build efficiently allows you to live quite lavishly for about the same energy cost. Now, of course, you can still punish yourself if you want. I say that in jest, but it's something worth considering. Anyway, I thank you for your time. This was a brief presentation. And if you have any questions afterwards, you can reach out to me. And I'm going to turn the thing back over to our esteemed moderator, Larry.
Thank you, Zach. That was fun. Actually, I'd like to thank all three presenters. You've done a really good job. You've given us lots of information. I want you to understand this is a pre-recorded session. And so if you have questions for any of our presenters, each one gave you their contact information. So please contact them directly and ask away. Thank you very much. Are there any questions that we each have of each other?
Carlos, I was really interested in your it seems like you've got a hybrid system, both one that runs off of grid power or that could be running off of solar. And it looks like you're doing a similar thing where you're running a heat pump to make up your heat for the bulk of it, with photovoltaics providing an offset rather than just grid tie. And I guess my question is, have you ever considered beyond that design? Have you ever tried adjusting the tank size, choosing a larger tank for the purposes of coasting through when energy is abundant, and you can make a kind of a storage, like a storage reserve that you can coast through, and rather than having to make it on the spot?
Well, you're right on the spot there. The reason we chose the 80-gallon was because we knew that larger storage is more beneficial to store solar energy. So it acts as a battery, if you want to put it that way. So by going from 50 gallons to 80 gallons and imposing a larger load, say 60, 70, 80 gallons per day for a larger family or for a multi-family housing, then that makes the compressor runs longer and also utilizes the solar energy available in its entirety, as opposed to shutting down at 12 in the afternoon and then you're basically not using the energy to heat water. So yeah, the basic concept here is to increase the efficiency of a compressor, of a refrigerant unit, so that as to, instead of consuming 500 watts, you're consuming 100 watts or less, or 200 watts, depending on whatever the sun is doing. So yeah, I agree with you. I mean, the larger the storage, it doesn't matter if you don't meet all of it, but you are making the compressor run a lot more efficient, because you're basically pumping solar energy into the compressor, which is into the refrigerant compression cycle, which is the most efficient way of heating water. So yeah, I've envisioned that if any manufacturer supports this endeavor, you can basically have two heat pumps, for example, and even if you have just two solar panels, you can just turn one heat pump on and one heat pump off, depending on what levels of energy storage you want in the tank. But again, the point here is to use every single energy generated by solar modules and make the compression, the refrigerant compressor run more efficient.
Great. Now, I have a question for Henry. Your presentation made it clear that monitoring can show as-built faults, when things are piped wrong or other stuff. So much of this boils down to what quality of installer, what quality of maintenance do we have? Has it been difficult to find people that can keep these complex systems running?
I think it may start off with the installer service person who actually has the ability to read a manual. I mean, it's not just a joke. It's an American. We don't have the reputation of reading manuals very well in this country. And many of the controllers that we use have dozens of different system arrangement possibilities, but they're left in default, which means somebody didn't change it, which means somebody didn't really understand it. When they talk about green jobs and all that kind of development, like we need more education for green jobs, we just need basic education. If we could have science education of 8th grade level, we'd be doing great. It's sort of like what your program that you and Zach did. It requires understanding little basic heat transfer, and a lot of installers don't understand, or people don't understand until they get burned. They don't believe it works, and it's an issue. I mean, they're not that complicated. It's just that they need to be done right. And I think that we have, in this country, we've gone too much towards residential credits, and it hasn't allowed the industry to scale very well. So that's why I'm more of an advocate these days for commercial systems where there's a large enough system, and then it will bring the production high enough so it gets the cost per square foot of collector down. Your nice, I mean, a nice non-pressurized plastic tube on a roof is good. It's a function of area. So that if that was made if there was an absorber plate that was a pressure absorber plate that was like a pool panel, only ran under pressure, that was freeze tolerant, it would be a little easier to deal with than your coil that way. So that it would be the same function.
Yeah, actually, Zach, I think your system is working at what, 50 psi? What is the pressure?
It's running at the standard pressure of the system. There's no low pressure system in there. It's running at the actual water system pressure for the tank.
No, I got that. It just meant that if there was a pool panel that could do that, run at pressure, at street pressure, that then it would be able to wet a wider square footage with less. I mean, it's a little cumbersome with coils compared to a flat section, but the things that flats are made for are not really intended for high pressure. And I wouldn't want to have a street pressure pool panel on my roof. Just that it might be that I have to go up there and deal with it. That's
precisely what I don't want to do. And
I get
that's
that.
precisely why, I wanted to make sure that my hope is that 25 years from now, I still won't have to go up, and that's fine by me.
So no joints on the roof, really good, that way.
And scalable in the sense that you could put a lot of them on if you wanted to, or you could make one huge one that was 30 feet.
Yeah. I have a Carlos question, if I could. I wondered if since I'm in a cold climate and I've been involved in some net zero energy buildings, and so that sometimes the air source heat pumps here have a problem of stealing from Peter to pay Paul, where if we put them inside the house, we're taking heat to put it into our hot water. But so I wonder whether other sources, some of the heat pump companies, I think, are working on some multi-inputs, being able to take heat from other waste heat sources, like exhaust air or exhaust water. And I just wondered if you were familiar with or have been involved with any of those.
I have personally haven't been involved. I do know that some of these heat pumps now, you can put them in cold climate mode where they will operate below 45 degrees Fahrenheit. I don't know how low you're talking about. In terms of heat pumps that are made for cold climates, the Sandin unit, which is CO2, utilizes CO2 as a refrigerant, is made for that purpose.
Right.
A lot of people have talked about doing what you're saying, that taking another process and somehow supplying that heat into a cold climate heat pump, but I haven't been involved in one either. And unfortunately, here in Florida, we haven't had much climate to test something like that either. I mean, I would love to have somebody take the system that I've been developing and put it up in the northern climate and see how it behaves.
Good. Great. Thank you for your presentation.
Thank you.
Okay, well, I think we've done it. Our time is up. Thank you all. This has been fun.